All right, if we could get started. If everybody can take their seats. Fantastic. Whew. Well, we finally did it. We're finally here. This has been a great preparation. I cannot thank you all enough for coming. Welcome to Norwich University's Todd Lecture Series, named in honor of the late U.S. Army Major General and Norwich President Emeritus W. Russell Todd, class of 1950, and his wife Carol. This series celebrates their dedicated service to both Norwich University and the Northfield community. We are pleased to offer this event free of charge to the Norwich faculty, staff, students, and greater Vermont community. Founded in 2008, the Todd Lecture Series is made possible through the generosity of Ellen and John Drew, the Todd's daughter and son-in-law, alongside the Drew Foundation. Tonight, we're excited to welcome our keynote speaker, Dr. Nicola Fox, Associate Administrator of NASA's Science Mission Directorate, and a personal friend of mine. Dr. Fox exemplifies our university's Go Beyond spirit. Since joining NASA in 2018 as director of the Heliophysics Division, she has led a world-class team dedicated to understanding the sun, Earth's most vital star. Her leadership has been pivotal in studying key space phenomena and enhancing situational awareness for astronauts, satellites, and robotic missions as they navigate the solar system. Additionally, her work in space weather research helps the U.S. government predict events that could disrupt radio communications, GPS accuracy, and even electrical grids. An accomplished scientist, Dr. Fox has authored countless peer-reviewed papers and renowned for her ability to make complex scientific concepts accessible to diverse audiences. Her leadership fosters a strong sense of purpose and belonging within her teams. In recognition of her achievements, she's received the American Astrological Society's Carl Sagan Memorial Award in 2021 and NASA's Outstanding Leadership Medal in 2020. Before her role at NASA, Dr. Fox was the chief scientist for heliophysics at Johns Hopkins University Applied Physics Laboratory, where she served as project scientist for NASA's Parker Solar Probe, humanity's first mission to a star, that star being the sun. Her extensive experience also includes serving as deputy project scientist for the Van Allen probes and operations scientist for the International Solar Terrestrial Physics Program. Dr. Fox holds a BS in physics from Imperial College of London, an MS in telematics and satellite communications from the University of Surrey, and a PhD in space and atmospheric physics from Imperial College. Please join me in extending a warm welcome to Dr. Fox.
Thank you. All right, good evening, everybody. It is a pleasure to be here. Sorry, I'm a wanderer. I don't like to stand behind a podium, so you'll see me moving around a lot. But it's a real pleasure to be here with you tonight. I've had a really fun day. Apologies to anyone who's had to listen to me talk today. You can take a nap for a part of this, because you probably heard it this afternoon. But I thought I would start by telling you a little bit about me and how I got to this amazing job that I can honestly tell you is the best job on and off the planet, and I can prove that. And then tell you about the excitement of NASA science. And obviously, unless you have the whole weekend, I cannot tell you about every one of the missions. So I've picked some of my favorite ones to highlight. So you can tell by my funny voice, I grew up in England, and I did, as you heard, I went through college. I did physics. But I started off, my sort of fascination with space started at a very early age, about 8 months old, when Neil Armstrong landed on the moon, and my dad picked me out of my crib and sat me up, propped me up in front of the family TV and gave me a running commentary of what was going on. Now, obviously, I don't remember that, but it was very important to him that I knew where I was when Neil Armstrong walked on the moon, and this incredible thing. And throughout my childhood, he very much inspired me with just the excitement of NASA and the feeling that could there be anything better than working for NASA. But that didn't mean I actually ever thought it was a possibility to go do that. So I did my degree, and I did my degree in physics, and I struggled when I first went to university. I went from like a very small, you guys are very lucky. I've been to some of your classes today. You have very small classes where you get really good, like almost one-to-one work with your professors. For me, I went to a very big school, and I went from a very small all-girls school where I did my high school to this huge, like 250-person lecture theater where I was just like an anonymous head in a sea of undergraduates, and I couldn't figure out how to interact in this really big group. I was terrified to ask questions. I thought that people would think I was stupid if I asked a question, because clearly it meant I didn't understand something, and obviously as in my head everybody else in the room understood it and I was the only person that didn't. And so I kind of struggled with my first degree. I did my master's, and when I was doing my master's, because it was in engineering, I was continually told by my professors, hey, you ask the wrong type of questions. You think about why and not how. You think like a scientist. And so I went back and I did my PhD, and I was doing, towards the end of my PhD, I went to a conference in Alaska, and like everyone I talked to today, if you ever get an opportunity to go to a conference, take the opportunity to go to the conference, take the opportunity to present your work and have conversations with people, because you're probably about 50% of the way of getting your next job by doing that. So always take those advantages. And so I was excitedly talking about my work, and a scientist came up to me and said, would you be interested in a postdoc at NASA? And that is how I ended up here. I said yes, I would be interested. Tried to play it cool, but I did say yes, and I applied and I got selected. And so I started at NASA's Goddard Space Flight Center. From there I went to the Applied Physics Lab, where I was really lucky to work on a ton of really exciting missions. Professor Gaines just went through a lot of those. Some of those you'll see. Parker Solar Probe is the mission closest to my heart, but you'll hear more about that in the talk. And then I moved to NASA headquarters, started in heliophysics, and then in February of last year, I became the head of science. And so it's an amazing job that I love to do. And so that's kind of me, and that's how I got there. Can we have the lights down a little bit, because I think you're not going to be able to see some of my charts. Just because we're science-y, so they're very dark, but we'll see. Oh, you're trying, okay. No worries. You can, okay. Hang on. Turning it on. This is how you know I'm a scientist, not an engineer. Okay, see if it works now. No. I'm going to go and hit the button. All right. Oh, maybe it's that one. Is it that one? No?
I'm going to hit it for you.
You're going to hit that for me? Okay. Hit it. Okay. Maybe it's not. Maybe you may just get this one chart for the next hour. Oh, there you go. Good. All right.
All right. We'll do it together.
So thank you. So this is the kind of our guiding objective that we have at NASA. Exploring the unknown in air and space, innovating for the benefit of humanity, and inspiring the world through discovery. And it's something that we take really seriously at NASA. This is what we want to do. And there are days where you get sort of really tied up in the minutia of the jobs you do just because you're the head of science. Doesn't. Oh, yay.
There we go.
Okay, too much.
Oh, wow.
All right. I love it. Okay, nobody can leave. I can see the exits, just so you know. If you all try and leave, I'll be able to see you. And you guys in the front, you're all wearing white, so you can't. I can see you wherever you go. All right. So it is space. It is like the final frontier. So At least you can see the charts now. Anyway, so, there are days where you get kind of caught up in the minutia of what you do. Like, I'm looking at 300 budget spreadsheets and whatever else, and you just feel like it's a really tough day. And then you see this kind of inspirational goal that we have, and you realize that even though you might be looking at budget spreadsheets, you're doing it because we're exploring the universe. And so it makes it just a very... Oh my goodness!
It's not NASA technology.
Actually, you know what? The biggest problem we have at NASA is figuring out how to use Teams in a conference room. So trust me, I love it. All right, so let's go to the next chart. All right, so the way that we think about this in the Science Mission Directorate, so obviously in NASA we have the Exploration Science Directorate that really is trying to send our astronauts back to the moon and then onto Mars. We have the Space Operations, which looks after all of the astronauts that are on the space station. We have Aeronautics, it's the first A in NASA. So we have the really cool planes, the really quiet supersonic planes, and then we have the Science Mission Directorate. And so in the science, these are our three key themes: protecting and improving life on Earth and in space, searching for life elsewhere, and discovering the secrets of the universe. And all of the missions that I'm going to talk about and all of the missions that you're going to see in a minute actually address at least one, mostly two, sometimes all three. Wow, you're all awake now, aren't you? They're all like, oh God, I was just trying to take a nap down here. Okay, so that's the themes that we have. If we go to the next chart, I think you'll see the baby picture. Yes. So you know how your parents really like to show pictures of you when you're babies, and they're always really excited about how proud they are of you. This is my baby picture. So this is the one I like to show people. So this is the fleet chart for the Science Mission Directorate at NASA. There are 155 missions on there, so that is what I'm currently responsible for. They're split into 5 main science disciplines. If you see everything that's in green, that is Earth science. So we have a lot of missions looking and studying our own planet. Anything in blue is planetary. In blue is astrophysics. Anything in purple is planetary. Orange is biological and physical sciences, and you'll see most of those experiments take place in microgravity, so they are on the space station. And then yellow is heliophysics. This is a very diverse portfolio, so we have a lot of missions that are still kind of PowerPoint charts and still being designed and still in their very early phases, all the way up to missions that have been in space for 47 years. That would be Voyager. And then I will just call out today is the birthday of the WIND spacecraft. It turned 30 years in space today. So we have, a very, very sort of, some of them have been in operations for a long time. Some are still waiting to be launched. We also have everything on here that goes from the size of like a CubeSat all the way up to the James Webb Space Telescope. And so it's a very, very diverse portfolio that covers everything that we want to look at, and still a lot more to do. Next chart, please. Thank you. So I'll start with our own planet. When I like to ask, particularly when I'm talking to kids, which is your favorite planet? And everybody always names all the planets, and nobody ever picks Earth. And yet it really is the most important planet. It should be our favorite planet. It's the one that we live in, and it's the one that every single thing that's happened in history, every person, every event has happened on this planet. So it is an extremely important planet for us. We have over 20 missions that are focused on looking at Earth. We look at all of the really key different criteria in the climate change issues. So we look at how mass is transferred around our planet by water. We look at the quality of the air we breathe. We look at what's in the clouds. We look at aerosols. We look at the quality of the water, the health of the oceans. We look at intense weather and how that changes. We look at how mass, how land forms change. And we do all that because they're all very interconnected in the climate research that we want to do. So we also work very closely with a lot of our sister agencies, and so we look at the Earth from the ground up as well as from space down. And of course, we have incredible models and climate models that we use to help us to predict these really intense weather events. If we go to the next chart, this is one of our new missions that we launched. We launched this in February of this year. This is PACE. So this is the plankton, aerosol, cloud, and ocean ecosystem. And it's really getting at the fact that all of these things are really connected. And so in order for us to really understand how our planet is changing, we need to look at all of these different things as one big system. With PACE, there's sort of two major objectives with PACE. One is looking at the health of the oceans, and the other is looking at the health of the air that we breathe. What you're seeing here, you're just looking at these three different views. This is one of our early images that we took from PACE. You can see the true color image there, and then the way we color it so we can actually look and focus in on different types of features. PACE has an instrument on it called the Ocean Color Instrument, and that allows us to look in unbelievable sort of detail at the spectrum of the ocean. So if you think about, if you have a Crayola color box and you have the one that has 8 colors in it and it's really boring, and then on Christmas morning you get the 256 bumper box of Crayola crayons, that is our Ocean Color Instrument. So we can actually look at very, very fine scale differences in the health of our oceans. We do that by studying phytoplankton. And phytoplankton are these, they're sort of, I like to think of them as the superfood of the ocean. They are like the major piece of the food web. They actually, everything kind of eats phytoplankton. Phytoplankton are also really powerful beasties. They help with the carbon cycle. They actually absorb carbon and give off oxygen. So they actually help with purifying our air also. With PACE, we can look not just at phytoplankton, but we can look at all the different species of phytoplankton. And what that lets us do is it lets us look at some of them are actually harmful. So some of them, we call it like a harmful algae bloom. You may have heard of something called the red tide, which can actually affect fisheries. It can affect the quality of the food that you eat. And it actually can affect all kinds of wildlife because everything kind of starts by eating these phytoplankton. And so we want to understand where these harmful species are, how they change, and how we can kind of contain them, and then also make sure that the food that we eat is very safe. The other piece of PACE, looking at the aerosols and the clouds, is really looking at the health of the air we breathe. Last year, you may remember, there were some terrible wildfires that happened in Canada, and we had smoke that came all the way down to Washington, D.C. And it shows that smoke doesn't follow borders, it doesn't care about the country, it doesn't care about the state. Smoke goes where smoke goes. And so it is really important that we understand the quality of the air that we breathe. And so this is just one of the missions that we have with Earth Science, but it kind of layers with many of the others. We have another mission called SWOT that looks at the surface water and the health of the ocean, so basically the rise and fall of the ocean. It looks at how mass is moved by changes in where the water is. And so when we have PACE that looks at the health of the ocean, with SWOT looking at kind of the surface of the ocean, we really can do these incredible studies by sort of layering the data together like an artist would layer paint on a canvas. Next chart, please. Okay, so biological and physical sciences. This is a really nice image taken from the space station. This is actually Vermont. We found one in Vermont, yes. And the bright that's Montreal as the bright city there. But it shows the Philadelphia, New York, Boston corridor, and then you can see it's up to Toronto and Montreal. So, but a nice view of Vermont from space. So the biological and physical sciences, we use that. This primarily does science in microgravity. So most of the time we're doing stuff on the International Space Station. We are also now looking at science that we want to do on the moon as part of Artemis. So we think about this from two different ways. Biological, really thinking about medical field, how we grow plants in space, but then physical, really focusing on quantum. We have a cold atom lab that is up on the space station where we can actually like suspend single particles and actually produce things like a Bose-Einstein condensate and actually have it suspended in space so that we can actually study these things. It will allow us to make sort of very big leaps in things like quantum computing. The things I'm going to talk about today are really the things that will advance fields like medicine and agriculture. Thank you. So this is just a shot of some of our scientist astronauts. People often wonder, hey, you can do all these things with robotic missions. Why do you still need astronauts? There are certain things that you actually need people and humans that can make decisions and can actually think on the fly and adapt immediately. We have a lot of stuff that we have our astronauts doing. This is just research in the microgravity environment that you can see here, but we're focusing a lot on things like how to grow plants in microgravity, what kind of conditions help plants grow better. So things like different colors of light, different wavelengths of light, and what actually allows a plant to grow quicker, and then what type of light actually allows it to be more nutrient dense. This is important for us at NASA as we get ready to have astronauts for much longer periods of time in space, and then eventually going on long duration missions to Mars. We want to be able to grow food and keep them healthy, and so this is important, but it also has direct implications for us here on Earth. A lot of people live in regions that is not easy to grow food. So it could be somewhere where it doesn't get any rain or somewhere where they really don't get much sunlight. So these very sort of difficult, austere, sort of extreme environments, and how can you actually help grow plants there? And so the research that we do in space is really directly applicable to that. We've also recently been able to grow, I wouldn't eat it, but we have been able to grow a plant in lunar regolith in some of the lunar samples that came back from Apollo. And it's the first steps of how could you actually grow plants on the moon. The other big thing that we do is a lot of medical research. And we send up something called tissue chips. And these are little tiny like pieces of human organ, pieces of like tissue of organs and cells from your body. We can put them into tiny little cells. The whole thing is about the size of the tip of a thumb drive that you would have in your computer. And we can put sort of these things in slightly different configurations, send them up into space, and look at how maybe like the efficacy of drugs, looking for cures. You can put put diseases in these pieces of organ, and then look at actually it's a sort of safe clinical trial of some of the new medications. Now you may wonder, well, why do I have to go to space to do this? Why can't I do that in a lab here on Earth? And it is because we need to get into a microgravity environment. Because cells in your body do not act the same way as cells on a bench. So when you take them out and you put them on a bench, they don't act the same way. But they do act if you take them up into microgravity. If you think about the beginning of your life, you spend the first 9 months of your life in a microgravity environment before you're born, right? Think about it. I'm going to give you a moment to think about it. Where were you for the first 9 months of your life? Right. So you're in kind of a microgravity environment, and your organs are sort of suspended somewhat in a microgravity environment, even inside your body. And so we need to get into these regions to really allow us to do some of this research. And some of the research we do is things like, why does somebody say, well, I've got a headache, I need to take Tylenol, whereas I would say Tylenol does absolutely nothing for my headache, I need Advil. Why? It's the same headache, possibly caused by the same thing, but our bodies just kind of change and process drugs in different ways. As we again get ready to send astronauts on long duration missions, mass is always a big issue. You don't take a whole pharmacy with you. You want to give them a really sort of personalized medical kit that you know is actually going to be able to treat whatever ailments they have on this journey. And so it's safe clinical trials, we're taking part in the Cancer Moonshot. We also did a lot of research on the efficacy of different COVID vaccinations, all done in microgravity with these little tiny chips. Fascinating stuff. I know, I love it. All right, next. Next chart, please, and we'll go to Artemis. So I just mentioned the importance of our astronauts. And so, as I said, I get a lot of questions sometimes, why do we still have astronauts? You've got these amazing missions. You can send them to all kinds of different places. Why do you need an astronaut? But this is a really great example of why we need robotic and astronauts working together. We can send robotic missions into areas that you would never send a human. We'll talk in a minute, but we've just sent a mission to the highest radiation environment in the solar system. There's no way you could send a person there. But there are things that you need that ability to actually make a decision on the fly, adapt, and change. And so here you're looking at one of our astronauts. So this is Christina Cook, who will go on Artemis 2. We had some very successful science on the Artemis 1 mission. We sent actually biological experiments in the Orion capsule that went around the moon. It's the first time we've had a human-rated spacecraft that went around the moon since Apollo. And so it actually had microgravity and also radiation that our astronauts will have to deal with. We sent samples of yeast and fungi and seeds, and basically to look at how the gene expression changes as you're in this microgravity, fairly high radiation environment. So we will have some great science on Artemis 2. We'll be announcing that in a couple of weeks. But we have some really great science experiments on Artemis 2. And then on Artemis 3, we actually have already selected the experiments that the crew will take down to the lunar surface. And actually some of those are biological and physical sciences as well, looking at how things will grow on the lunar surface. We also have selected a geology team that is working with the astronauts, kind of teaching them about the rocks they'll see and the samples that they're going to take so that they can make those decisions in real time of which are the best rocks to bring home. So it's a great example of how we're working with our astronauts to prepare them to do really great science when they get to the moon. The other big thing that we need to protect them from is space weather. So from like high radiation events. Some of you may have seen beautiful aurora recently. The sun is awake, it is very, very active, and it is producing beautiful aurora. With a very active sun comes a lot of space weather, and we actually have selected instruments that will fly to provide space weather forecasting and kind of radiation forecasting for our astronauts on the moon. So a lot of science with astronauts. So I mentioned solar and solar activity. Heliophysics is our division that looks after everything to do with the sun, everything from the very center of the sun all the way out to the very edge of our solar system, where the Voyager spacecraft currently are. Our sun, it continually, so you are in Vermont. Most of you probably saw a beautiful solar eclipse in April. When you saw the total solar eclipse, you saw the sun's corona. The sun's corona continually streaming away from the sun. It carves out a protective bubble for our whole solar system as we orbit around the Milky Way. So the sun's atmosphere actually protects us from the vagaries of interstellar space. And that is what we study with heliophysics. It also look at how we use our data to forecast space weather and therefore to protect humans and to protect the technology from things that are happening in space. If we go to the next chart, I will talk about my very favorite mission. And this is Parker Solar Probe. So this is a sort of artist's impression of what Parker Solar Probe will look like closing in on the sun. This mission is very personal to me. I was the lead scientist for this one. It launched 3 weeks before I left and started my job at NASA. But I have an incredible team on Parker Solar Probe that were just the best team that you can imagine working with. Parker is it's a historic mission. It was first proposed in 1958. And this was when a scientist published this paper saying, hey, I think that the corona, the sun's atmosphere, is continually streaming away, and he called it the solar wind. He was kind of ridiculed when he wrote this paper. People didn't believe it. It was not well accepted. However, it also sparked the thought that, well, the only way you can actually prove whether it's right or wrong is to send a mission into the sun's corona, so into that atmosphere that you saw during the total solar eclipse. 1958, we didn't have materials, we didn't have technology, we didn't have things that would allow us to be able to send a mission into this very high radiation, very dusty, super hot region. 3 million degree plasma is what this spacecraft is going through. So we launched in 2018. We're actually almost at the end of the mission. On Wednesday, we will do the 7th Venus flyby. So we fly by Venus, and we use it it's kind of like doing a handbrake turn. We give energy, so we do a gravity assist with Venus. We give some energy to the planet because we're very generous in heliophysics, and we actually use it to kind of slow down the spacecraft, and so it falls sort of gracefully towards the sun. So on Wednesday, we will do the 7th of those. That is the final one. And then on Christmas Eve, we will make the closest close approach, and we will go to within 3.83 million miles of the sun's surface. That may not sound very close to you, but if I put the Earth and the sun 1 meter apart, Parker Solar Probe will be less than 4 centimeters from the sun. So that is pretty freaking close. We will be traveling at a blistering speed of 430,000 miles an hour, which is about 118 miles a second. So that is how fast Parker Solar Probes. We've broken all kinds of records. Technologically, it is a very inspiring mission. It was also the first mission that was named for somebody during their own lifetime. So Eugene Parker wrote the paper in 1958 that inspired the mission. And he actually joined us at the launch. And so he's the only person to ever watch a mission named for him actually launch into space. And so we've taken amazing data, incredible science. The goals of the mission were really to explain why the solar wind happens, why this atmosphere that you see continually streams away, and why it is 300 times hotter than the surface of the sun, which has been a mystery for solar scientists for over 100 years. If you walk away from a campfire, you get colder, not hotter. If you move away from the sun, the plasma gets 300 times hotter, and it doesn't make sense. So why does this happen? And so these were the main goals of this mission. I'll tell you that what some of the things we found on our very first flyby of the sun, we found these very weird kind of S-shaped features in the magnetic field. In fact, when we first saw them, we thought the instrument wasn't working properly, went and checked that there was nothing wrong with the instrument, and then discovered, no, in fact, the magnetic field was kind of turning back on itself and making this S-shaped sort of feature in the solar wind. If you think about taking a really thick garden hose and twisting it, you actually have to put a lot of energy to twist that garden hose, and the first thing it wants to do is spring straight again. And so there has to be something very unusual that is causing these kinks to happen in the magnetic field. The closer we got to the sun with the sort of successive Venus flybys, the more of these features we saw, and they got bigger. And so, we knew these features were there, but it's difficult to measure how much energy they would actually, as they straighten, they would actually put into the solar wind. Earlier this year, we had a really lucky, fortuitous conjunction with Parker Solar Probe really close to the sun and the European Space Agency's Mission Solar Orbiter further away, but they were on the same field line. And so we were able to measure the S-shaped curve with Parker Solar Probe, and then about 2 days later measure the same feature with Solar Orbiter and look at the difference in the amount of energy. So we know how much energy is now going into the solar wind, and so this is sort of part one of the science that we're trying to do with Parker Solar Probe. But anyway, super cool, coolest, hottest mission under the sun, Christmas Eve, fingers crossed for me, please, because I will tell you that when you're studying the sun and you go really close to the sun, you often lose contact with your spacecraft. And so I have 11 days of terror because it will disappear behind the sun, and it's a large glowing body, it's a big star, so you can't actually communicate through it. And so I will get a signal, I hope, I will get a signal from the spacecraft, and it will say I'm fine. It's called a green beacon, and it will say I'm fine. And then 11 days will go by, and then it will come back out the other side, and I have to hope for the same green beacon tone. And if it's a green beacon and we check the solid state recorder on the spacecraft and we know if the instruments have taken all the data, if the solid state recorder is full, it's a good day. So I will be waiting for 11 days, and the mission ops folks at the Applied Physics Lab, because they know I worry about the spacecraft, it's like my baby, they will send me a green heart by text. And I look for the green heart, and when I get a green heart, I start breathing again. So think of me Christmas Eve. I'll be halfway through 11 days of terror.
I'm going to send you a green heart.
Don't you do that. No, only send me a green heart if it's a real green heart. Okay, you can send me a red one. She's going to mess with me on Christmas Eve. All right, so planetary science. So the other reason that we study our sun so closely is it's a star, and it's an average star. And if you do your astrophysics and you look at kind of the plot of how the stars all line up, we're right in the middle of the main sequence. We're a very ordinary star. But it is the only ordinary star that we know that actually supports life. And so it becomes a very extraordinary star, and it's one that we really want to study. And we want to study it because one of our goals, as you saw at the beginning, is the search for life elsewhere. And so if we study our own star and we understand our relationship with our star, it helps us look for, find the right kind of candidate stars and planets orbiting them in other stellar systems. But we also know that we think that there are signs of life, or there was life on other places in our own solar system billions and billions of years ago. So around the time that our planet was forming, we think that there may have been other life, microbial life on other bodies in our own solar system. And with planetary science, that's one of our goals, is to go and look for different signatures to see if life could have been supported on other moons in our own solar system. Thank you. And so last month, we launched the Europa Clipper mission. And Europa Clipper is going to the moon, Europa, which is one of the large moons of Jupiter. And this is a really nice image here that was taken by the Galileo spacecraft of Europa. Europa has got a very thick ice crust on it, and we think that underneath that ice crust there is like a saline ocean. One of the things we're looking for as we fly by it, sometimes you see plumes coming up, kind of coming through the frozen surface of the moon. What we hope to do is fly through one of those plumes and actually look at, what is in there. We're looking for sort of what we think of like as the four main ingredients of being able to support life. One is water, one is energy, one is chemistry, so something that's active, and one is stability. Because obviously if you look at something that's changing all the time, you're unlikely to be able to actually sustain life on it. So you need something that's very stable. So while we do not expect to find, it's not a life detection mission, we do not expect to find life on Europa. What we're looking for is what were the conditions in our planet like before life started? So what was it like when life was forming here on Earth? And if you think about it, like life is very noisy. We have kind of infiltrated everything around us. It's very hard to sort of think about or research what conditions were like here before life started. You can go to the outback in Australia and you can find some of the oldest rocks on the planet, and you can do some sort of astrobiology there, but it's really hard to be able to sort of figure out what prebiotic life would have been like. So that's what we're doing with Europa Clipper. Also, of course, studying the general conditions of this very beautiful moon. And if we go to the next chart, an even more ambitious mission that will launch towards the end of this decade is Dragonfly. So Dragonfly is like a drone. It is a rotorcraft. It is an octocopter. So it has 8 blades. It's about the size of a small car. And this mission will go to Titan, which is a moon of Saturn. And this is a nice image. It's one of the best images that we have of Titan right now. This is a really challenging mission. This will travel to Titan in an aeroshell. The aeroshell will open and that thing has to start flying immediately. It will fly and hover. It will land in different areas on Titan, take data, and then take off and hover and land in other places. It's about just over a 2.5-year mission, so we hope to cover a very diverse regions of Titan. Titan is a really interesting moon. Like we have a water cycle here on Earth, Titan has a methane cycle. And so you can sort of imagine like lakes of methane and waterfalls of methane and beautiful things. We also want to go to sort of dried up lake beds where the methane has been but isn't there any longer. And again, we know that there's chemistry, we know that there's active, there's carbon, we know that there's a lot of the building blocks of life on Titan. So even though it couldn't support life now, the moon is way too cold, what was it like and could it have supported life back as the solar system was very young? It's a very exciting mission. And then a little closer to home, on the red planet, we have our Perseverance rover that is currently driving around Mars and taking core samples of all different scientifically selected locations. And so earlier this summer in July, we took this really interesting sample. And this is, you can see some features. They're a little hard to see with the lights on, but you can see that we're calling them leopard spots. And you can see these are sort of sulfurous veins. This is in a particular rock formation in an area called Chevier Falls. So Perseverance has been in Jezero Crater, which is kind of a dried up riverbed where we think, when there was water on Mars, it was a very active river. The rover has kind of climbed out of the riverbed and is up sort of on like the rim of the crater. And is still taking really great samples. So this, what you're looking at, you can see sort of the red, so you can see the sulfur, and then this is actually a sort of reddish, rusty color. This is hematite, which is the mineral that gives Mars its distinctive red color. But you can see this, I don't know how well you can see it, but where you can see the leopard spot there, it's like white with a little dark circle around it. And that is usually indicative if we look at biological systems here on Earth. When you see that kind of feature, it's because some sort of biological process has happened. In this one, you can see a black line around it because the hematite has actually reacted with the sulfur, producing different chemicals. That is very similar to sort of what it actually shows is some sort of chemistry actually happened. It is certainly consistent with possible interactions with microbial life. It's kind of the chemistry and the energy that would get released and could be a sign of microbial life. So while no life on Mars, this is a really, really exciting sample. We have done everything that we can on the surface of Mars. We have studied this with all of the instruments that we have on Perseverance. This was actually, the image you're looking at here was taken with the Watson camera. And this is the core sample. So once this was seen with the camera, we studied it for a little while. Then the drill went down, took the core sample. It's inside a tube right now in the belly of Perseverance. My things to do on my things to do list, figure out how to go get those samples and bring them back from Mars. So it'd be very, very important for us to bring samples back. In the Apollo days, we brought tons of samples back from the moon. Some of them we recently opened 50 years after the samples were taken and have been able to do unbelievable science with those samples that you could not have done 50 years ago because we've actually matured our technology here on Earth. And so when we started looking at Apollo samples back sort of 50 plus years ago, essentially had a nice microscope that you could look at them with. Now, if you go to Johnson Space Center, you will find there are mass spectrometers about the size of, a classroom, that you can actually do this really, really high precision science. And so we want to go bring back our samples, do really great science with it, but also to preserve a lot of the samples to inspire the next generation and the next generation of scientists and explorers to do even greater things. So that's excitement on Mars. Astrophysics. All right, we're nearly at the end, guys, don't worry. So in astrophysics, we explore the universe, and we really think about pushing the boundaries of what we know about our cosmos and about sort of the universe around us. we have these very powerful telescopes in different locations looking at the universe in different ways. And this kind of gets, again, at the importance of looking at things from different perspectives, which you can kind of take in your everyday life as well. It's important to look at things with different perspectives and in different ways. And astrophysics, when we look in different wavelengths, we really can see unbelievable features by putting sort of these cameras together. If we go to the next chart, this is actually one of my favorite images. This is a spiral barred galaxy. And it is, astrophysicists do not have great imagination. The name of this image you can see is NGC 1512. Yeah, so that's about as good as it gets, guys. NGC 1512. Sorry to all the astrophysicists in the audience. But it's hard, again, it's hard to see in this light, but the top sort of quarter, so if you put a diagonal through here, the top of this image is taken by the James Webb Space Telescope. The bottom here is taken by Hubble. And the reason that they look different is you're looking in very different wavelengths. So James Webb looks in infrared, with Hubble looking in visible and ultraviolet. It is the same, it's essentially the same image. It was not taken at the same time, but astrophysical scales are pretty decent, so you can take it a while apart, and it hasn't changed very much. If you look at the top, you can see this sort of jagged, very vibrant, bright features, and in the bottom, it looks much more sort of dusty and hazy. One of the reasons is that the dust, interstellar dust, absorbs light, visible and ultraviolet light, but it emits infrared. And so it's kind of looking at a different, you can look at the same thing from a very different way, and you actually see very different features. So by putting these images together, sometimes we overlay them, you can see really different things. There's another beautiful image of the oldest or the most distant black hole that was discovered recently, discovered by Hubble and then visited, or rather, viewed by Chandra in X-rays, allowing us again to see things in very, very different ways and see features that you can't see with just one single telescope. What we do in astrophysics is we also build on the legacy of the missions. So what we learn from Hubble, we then apply into the next missions and the next missions. We are getting ready, but getting close to launching the next big astrophysics telescope, which will be the Nancy Grace Roman. And that looks, that is going to do like whole sky surveys. It has an absolutely massive, massive field of view. And it will be studying dark energy and dark matter. It will carry with it a novel technique, a novel instrument. It's a demonstration instrument of a coronagraph. And so sometimes if you look at images of our sun and you want to look at the corona, we put a disk in front of the cameras. It blocks out the light of the star, and you can see, just like a total solar eclipse, you can see the corona around it. This is actually going to block out the light from very distant stars and allow us to look at exoplanets that orbit those stars. The mission after that will be something called the Habitable Worlds Observatory. That is the goal for that mission is to find life elsewhere in the universe. And we will do that with, using the wavelengths of Hubble. It's a telescope the size of James Webb, and it will have a full-up coronagraph just like Nancy Grace Roman. So again, building on the legacy, using what we learned from one mission and rolling it into the next one. Okay, yes, thank you. So, before I finish, I wanted to just explore some other areas that we do in NASA science. I've told you about some of the interesting missions that we have, but I always like to do the sort of the picture a scientist experiment. You can close your eyes, but if I asked you to picture a scientist, what is it? You have to open them again if you close your eyes, guys, okay? What does a scientist look like to you? If you think about a scientist, what do you see? Maybe you see somebody you know, maybe you see somebody in a white lab coat with gray hair and big glasses. Maybe you might see somebody who looks crazy. Maybe you saw Einstein. But the thing is that whatever you see as a scientist, did anyone picture me? No, well, apart from you, Michelle, but probably no. Can we go to the next chart? So, here I am looking in a sort of a more typically, I'm looking quite smug with myself actually there, but either that or I'm serving meat on the deli counter. I always think I look a bit like that too. But I'm actually standing in front of Parker's solar probe, and it's in the clean room, which is why I look so silly. But that's a sort of a more typical sciencey picture of me. But, whoever you thought of when you thought of a scientist, the thing we all have in common is we're all human. We all like asking questions. And, we all have different lives and different things. Now, if I walked up to you, or you came up to me at a cocktail party, and you said, you introduced yourself, and I said, oh, hi, my name's Nikki. I have 2 kids, 15 and 17. My son loves to play lacrosse. My daughter's a really gifted singer. You can totally interact with me. Because, you might be a parent, you might like lacrosse, you might like a good karaoke sing. There's going to be something that you can find to actually engage with me. But if I say I'm a scientist, you may not want to. My God, if I said I was a space plasma physicist, you'd probably get a call on your phone immediately and have to leave the room, or go and find somebody much more exciting to talk to. But in fact, I'm actually the same person. So even though I am genuinely a space plasma physicist, I also do have to worry about making dinner, school pickups, and getting college applications finished for my son. So we're all very, very similar. So we go to the next chart. So this is a shot of some of the women of NASA. But again, it's not just about So I take very seriously in my job the ability to inspire the next generation and to actually explain the science and make the science that we do very accessible to everyone. Everybody is a scientist. So you don't have to, everyone thinks, oh my God, you must be really smart to be a scientist. Well, trust me, I'm not, but I am a scientist. And what I like to do is I like to ask questions. And that's what makes you a scientist, is the curiosity about the world around you or about life around you. And if somebody asks you the time, do you have the time on you? You look at your watch, you take data, you make a conclusion, and you present your result. So it's 7:51, by the way. So that's the scientific method. That's all that is. That's exactly what we do in science. We just maybe use telescopes or the James Webb Space Telescope instead of an Apple Watch. But we do the same. We do experiments all the time. So everybody really is a scientist. And it really is about making people understand that there's nothing scary about being a scientist or an engineer or any of these other fields that everyone thinks, wow, you must be really smart to do that. And studies have shown that students who actually work in science and engineering feel that they are doing something to better life and better the world around them. And they're far more likely to stay in that if they have that kind of feeling that what they do really matters. Go next chart.
I think I did it by accident.
Oh, you did.
Is that right?
That's
Sorry.
all right. No, never mind. We're getting on to this. So this, with this theme of how do we make people sort of see themselves as scientists and engineers and see themselves with these, these amazing careers that we all enjoy. And you may be familiar with diversity, equity, inclusion, and accessibility. At NASA, we refer to it as IDEA, not just because it sounds cool, but because one of our main things that what we try and do at NASA is to foster a sense of inclusion. You can talk about the need to have diverse teams, you can talk about the need to hire people that look differently, but if you don't make them feel included and you don't actually make them feel like that their opinion matters and they can be themselves, they're just going to leave, and you didn't actually move the ball forward at all. If you have teams where everybody looks the same, sounds the same, and thinks the same, guess what you get? The same. If you have people that come with all different perspectives and different ways of doing problems and different ways of finding solutions and different life experiences, then they are going to be the strongest teams. But the only way that really works is for people to see themselves in that team and feel that when they are actually expressing themselves and giving you ideas, that you actually want to hear it and you're taking it seriously. So this is something we have a huge, in fact, inclusion is one of the core values at NASA. Are we making sure that our teams are inclusive so that we can have the highest possible performing teams, because what we do is really hard. That's also a shared goal, by the way. When everybody has a really hard problem they work on together, that really does form an incredibly tight bond. We'll go to the next one. But I want people to see themselves in the ability to do science. So one of our the big programs that we have right now is Open Science. We have actually courses that you can take. If you actually look at NASA Open Science, we have an online course that you can take to help you actually be able to use our data. What we want to do, I mean, again, we want to get away from this idea that you have to be super smart to be a scientist, and oh my goodness, what I do is so complicated you'd never understand it. We don't want anyone to think that. We actually want to lower the boundaries of entry and let everybody know that NASA science is there for everybody. So I encourage you, if you're interested in doing science with us at NASA, there are several ways that you can get involved even now. I recommend looking, in fact, we've got Q codes. If I actually got out of the way, you could probably see that there was a Q code on there. But you can actually go there and take some of the training and learn how to use our NASA data, which is very important to us. That 2023 was the year of open science, and we really embraced it with trying to make sure that our data were not just available, but actually usable. I can make data available, but if I don't explain it to you, you can't use it. And so this is really about how we let people come in and share the joy of NASA science. And on the next chart, another way you can we do this is with our citizen science. We actually have a very vibrant citizen science program at NASA. You can anyone can apply. You just basically need a computer and curiosity, and you know a sort of a thirst to actually find out more about what we do at NASA science. But if you saw the Aurora recently, there is a citizen science group called Aurorasaurus. If you take pictures, you can send your pictures in. It's a global, worldwide network that is studying the aurora and looking at how the aurora changes. We had an incredible group that worked during the eclipse. We had citizen scientists all the way up the entire path of the eclipse doing experiments in real time, things like what happens to the atmosphere when the sun goes away suddenly. You don't have a nice transition from day to night. It just gets switched off. What does the atmosphere do? And how could we recreate that if we needed to? There was a whole group of citizen scientists that do that. So again, you can apply for grants. We have many grants that we give to our incredible citizen scientists. You do not have to have a PhD. You just have to have a laptop and a curiosity and a kind of desire to do NASA science. Okay, and then even if you don't want to be a scientist or an engineer, though I'm shocked that you guys would not want to be a scientist or an engineer, by the way. But you can, if you take almost any career path that you can think of, you can do it in a NASA mission. You know, obviously we have every kind of engineer you can think of, and we have a ton of scientists that work, but we also have, our business professionals, our IT professionals, our lawyers, people that do the budgets, people that do our schedules, people that do the graphic design, people that do these incredible charts for people like me, people that visualize what the mission is going to look like, people that do all the computer modeling that go sort of underneath it. It is hard. People that are really good at telling stories, and people that are really good at translating and working with, our STEM professionals that go and actually produce products for kids anywhere K through 12 and into college. It is hard to think of a career path that would not enable you to work at NASA. So even if being a scientist or an engineer doesn't call out to you, but you like the idea of working on a space mission, there are loads of ways of doing it. Up there you see astronaut Jessica Watkins. She actually did geological and environmental science, and she has a PhD in basically landslides on Earth and Mars, which you wouldn't necessarily think, oh, that's the sort of thing I'm going to do if I want to be an astronaut, but it makes her an incredible specialist, a scientific specialist, for the missions that we have, so the science that we do on the ISS. Also preparing us to, be able to do science on Mars, where, we actually do want to study landslides on Mars. So there's really, it's a very diverse community that it takes to get a mission into space. All right, I think we're nearly there. Yes, thank you. So.
Give some time for a couple of questions
I do,
from the
yes.
audience.
Yes,
Yeah.
I kind of hope that you can see yourself somewhere in the science or in this field, or that you're inspired to at least do NASA science.
We got some questions.
Yeah, we have
Look
questions.
at this.
Wow.
My goodness.
All right.
All right, here we go. Here we go.
All right.
Yep.
Good evening. I'm Casey Chastain from Orlando, Florida. So I saw all the Space Coast stuff growing up. One of the questions I have is, so with Europa and like a possibility of it like containing like livable conditions, is it possible that in the future we could ever see a formation of life on Europa?
So it wouldn't have livable conditions now because it's the solar system's expanded and it's cool. It's too cold there. We call it the snow belt because it's just too far away from the sun to be able to support life now. What we're looking at is, does it have the building blocks of, could it have supported life at one point? And that actually helps us when we're looking for life in other stellar systems to look at, okay, maybe you don't just need the Goldilocks planet, maybe there's other places that could also support life. But it's really trying to figure out what our planet was like as life was forming. So it's not, we don't expect to find life there because it's now too cold. But what we're looking for is there prehistoric life? Or, is there like signs of prehistoric life there?
The man in the awesome vest over there, please. Yes.
Thank you. I made it for space conferences. I wanted to thank NASA. This is my 21st year in a row of receiving NASA grants, which allowed me to build the first successful university satellite in the Northeast. And for fun, the first 3 weeks I was teaching at Vermont Tech, Voyager 1 and Voyager 2 were launched. And many other events have happened when I'm teaching those particular subjects. So it's been very nice to be able to talk to real world stuff that way. Thank you.
All right.
Did you watch with us when we reestablished communication with Voyager 1 recently? We lost communication with Voyager 1. I said I wondered if you actually followed when we took a Herculean effort to reestablish communication with Voyager 1 earlier this year. Yeah, it was. I don't think I've ever cried so much at work when they called me and told me that we'd lost communication with Voyager 1. And to give you a perspective, it takes about a day to get a signal from Earth to Voyager 1, and then a day to get the response back. So it's a light day away. If you think about that's how far it is. And I don't know, I personify spacecraft, and so I think about them as like it's so cold and they're so far away and they're all on their own and there's nothing out there. And yeah, so when we lost communication, I was devastated, but it took an incredible team of scientists and engineers. People came out of retirement and came back to actually help us reestablish it. And then when they called me and they said, we got it back, I was just a hot mess in the office. I really was. Yes.
Go ahead.
Good evening. My name is Todd here from North Louisiana.
Speak up.
I want to ask, when you were talking about the plasma from the sun's magnetic field going around it, I want to ask, did the plasma move around the magnetic waves because the field is stronger than the plasma, or did it move around or did the plasma move around because it just flows freely that way?
That is a phenomenal question. Right, so the plasma follows the magnetic field lines. It's essentially stuck on the magnetic field lines. When you are close to the sun, the magnetic field rotates, so the sun rotates, and the magnetic field rotates with it like one solid body. And so that's close to the sun. We see rotation, and we see the plasma moving with the magnetic field. Somewhere in this region that we're trying to study with Parker Solar Probe, the magnetic field, the plasma itself gets so energized that it actually can pull away from the giant pull of the sun, and we call it a frozen-in thing. It's like it grabs the magnetic field and it takes it with it. So when it's close to the sun, the magnetic field is dominant and it guides the plasma. But in this region, the plasma gets so energized, it becomes dominant, and it pulls the magnetic field away with it. So the magnetic field moves radially away from the sun. Because the sun is rotating, it looks like a garden hose, kind of like a sprinkler. It makes a spiral called the Parker spiral. But that's the big transition when it goes from the magnetic field being the stronger of the two to the plasma being so energized that it takes the magnetic field where it wants to go? That's a really great question.
Wow, yeah,
Thank you, ma'am.
thank you. All right, another question?
Good evening, ma'am. I also have a question about the sun.
Okay.
So considering that it seems to break the second law of thermodynamics, what is your personal idea on why the atmosphere of the sun seems to grow hotter the further away it goes away from the surface?
Yeah, so it comes down to, there's two different camps. There's a group of scientists that think absolutely everything that happens is because of turbulence. And there is another group that think it is all because of magnetic reconnection. So magnetic reconnection is when field lines break and then reconnect. And when they break, they let a lot of energy out into the solar wind. Eugene Parker was a very close personal friend of mine. He believed it was nanoflares. So nanoflares, so you know when you have a really big event, really big solar event, you see like X-class flares and they give a ton of X-rays. So what he predicted was that these things were going on all the time, but very, very small. So that, and you can't see them because, you know, the sun is really bright and it's really hard to actually image them. And so that's one of the reasons we need to get really, really close. So I will say that my personal hope is nanoflares because I love Eugene Parker. Solar Orbiter has seen something that we called campfires, where you actually see little blooms of light close, much lower down in the corona. I think those are nanoflares, so my personal thing is we're going to find it's nanoflares. Then we get into, are the nanoflares caused by magnetic reconnection or turbulence? I'm going to go with magnetic reconnection because my thesis advisor, my thesis advisor's thesis advisor discovered reconnection. So that's where I'm going with my hope. Reconnection and nanoflares. Okay.
All right. There, and then what I'm sure you can do is maybe people can come up afterwards
Yes,
and ask you some
absolutely.
personal questions, because I know they're tired people, young
Yeah.
people.
And it's a Friday night.
It
I
is.
can't believe you guys
But
did it
actually,
a
we need to
Friday
keep them
night.
here so they don't do nefarious things. Okay, but anyway, go ahead. Yeah.
Good evening, ma'am. As time progresses further on, we keep putting more and more satellites into the sky, which is causing observatories to have streaks on the camera lens, which is making it more and more difficult to get accurate images of space. What's NASA's plan to counteract that while still managing the amount of satellites we're putting into orbit?
Yeah, so there's a very easy answer to that, which is that we study space from space, and so our telescopes are not affected by it. However, our ground-based telescopes that are National Science Foundation are definitely struggling with it. I mean, it is something that's not going to go away. We actually, you know, while it's very difficult for us to do astrophysics, it's also great for all the other reasons that we have it up there. The bigger problem is with proliferated LEO, as we call it, with the ton of spacecraft that are there, is orbital debris, so debris in space, and making sure that we keep space as pristine and sustainable as possible. And so we actually have a sustainability strategy to try and deal with not cleaning up space, but actually, you know, making sure that we don't have collisions and making sure that we do that. Honestly, for astrophysics, it's really tough, and without regulations, which NASA's not a regulatory body, we can certainly say, yeah, it really sucks. We wish we could see the sky better. There's actually nothing we can do about that. But certainly we support our scientists who are, you know, talking about the need to keep space empty. I honestly don't know what we're going to do about it because we rely on those spacecraft so much for all of those things. But there's actually NASA as an agency. There's nothing we can do about that. What we can do is try and encourage people to look after their spacecraft while they're in space. If they're going to deorbit them, have a re-entry plan that actually makes as close to zero debris as we can, which will also help.
Thank you.
All right, we'll do one last question, then we'll bring the other two up for personal
All right.
questions. Yep.
Hi, my question was, how does NASA, the agency, prioritize or deem other missions more important than others?
So In a broad way, the way that we prioritize our missions is the National Academy of Science, Engineering, and Mathematics gives us what we call a decadal survey. And each one of those 5 divisions they talked about, each one of us gets different decadal surveys. And so it's a big community effort. It takes a couple of years to actually write a decadal survey, but it prioritizes the science that we will do over the next decade for that given discipline. The way we prioritize missions is usually by the decadal survey, like which one you should do first, which one you should, what order you should do them in. The other answer to that is we get our money appropriated from Congress, and a lot of that comes with instructions on which ones are more important, which ones have the support, and which ones don't. And so we have to sort of move. We have to take what we're grateful for every penny, by the way, but the money that we get, we have to spend it wisely. So in a broad sense, it's what the community tells us is the most important, mixed with where the support on the Hill is.
Thank you.
All right, well, one last round of applause for Dr. Fox. Thank you. Thank you. Enjoy the night. Thank you, everyone. For those of you who had a couple questions, I'm sure Dr. Fox would be more than happy to come on up. So come on through here and